Oh, okay.
Yeah.
All right, let's try again. Hi, everyone. You want to do something else?
Nope.
Okay.
Or just yeah, they can see him.
Okay. I apologize. That's what I would say. I apologize to the Zoom folks. I'm kind of a pacer, a wanderer. I'm going to do my best to kind of stay here and also focus on you guys. But, you know, this is how it goes. So, Igneous Rocks of Arkansas. Darsha asked me to give this talk because apparently I think I said on my website or something like that that I know something about Igneous Rocks of Arkansas. In truth, the truth is when I told you the story of coming here for this job. So I landed in the plane and Jeff, who would become my department chair, picked me up and he said, and I said, hey, I saw those big, huge quarries when I landed. Is that limestone? And he looks at me and he says, no, that's all cyanide. Yeah, you get the joke because I had already failed the first test, which was to not recognize the igneous rocks in Arkansas, literally on the drive from the airport. So no, he said, no, that's all cyanide. And I said, oh, that's really interesting because cyanide's a really unusual rock. We'll talk more about that. So I came to Arkansas actually not really knowing a lot about the geology of Arkansas and quickly learned that it's an incredibly diverse and interesting state when it comes to geology and a lot of other things, of course, too. But so what I want to do tonight is I'm gonna do a little bit of teaching because I can't help it. Okay, so forgive me. But I want to really break this down a little bit. Igneous Rocks of Arkansas. And I'm going to start with the really basic question here, which is, if this works, let's try it again. Space bar.
Right arrow key.
I did the right arrow key. Let's try this. There we go. What is a rock? Is that a rhetorical question? Does anybody have a sense of what a rock is? It's like you all know what a rock is because you've seen them. You've probably. So that's, most rocks, that's true, but not all rocks actually have to be made of minerals. So there's some examples. Anybody know, an example? See what I'm doing? Teaching. What's a rock that's not made of a mineral? Pumice is made of volcanic ash, which is a glass. So that's a really good example. It's actually not minerals. The other one that you probably know is obsidian, right? If any of you have seen the Shawshank Redemption, that's the, oh wait, I shouldn't give it away. Never mind. Anyway, so go watch that movie. It's a great movie. So, this is also a rock here. I think this guy. So rocks are coherent, naturally occurring solids containing one or more minerals, sometimes glass. Okay, so the rocks we're going to talk about mostly tonight actually contain minerals, right? And but there are some glassy things also in Arkansas. So anyway, I don't know if he really does contain one or more minerals and sometimes glass, but you can't do slides like this anymore without putting him in there somewhere. So okay, so there are actually two ways in which these minerals are held together. The first is what's called the clastic texture. And this is the one that's most familiar probably to most of you in this room because you live in Arkansas and this is most of Arkansas, right? Grains are stuck together by cement. So these are sedimentary rocks that we're talking about. So sandstones and conglomerates and things like that. Like I said, this is most of Arkansas, but who cares? Okay, tonight, no, a lot of people care. This is sedimentary are important rocks. But Darsha asked me to talk about igneous rocks. So that's right. Yeah, so that's what I'm going to do. So igneous rocks, the other texture that you can get is what's called a crystalline texture. So this is where these crystals interlock with each other as they form, like jigsaw puzzle pieces that lock together. And so this picture that you're looking at right now is a piece of granite on the left. And then what you're seeing in the other two images is a microscopic view of that granite. So let's see, do we have a pointer? No, it doesn't show up on that screen. But I'm just going to point, sorry guys. So these are all the different minerals that you're seeing. The gray in the middle is either plagioclase, feldspar, or quartz. I can't quite tell. The brown in there is mica, it's biotite mica. So this is sort of a sketch of that that crystalline texture. So we like that, and kids like it. So then the question is, okay, if those are our textures, what is an igneous rock? And we have to go back to the basics here, right? So this, you guys all seen this before? What is this thing called? The rock cycle, okay? You're like, well, there's country, there's no, I'm just kidding. So the rock cycle, this is sort of one of those governing or, basic sort of principles of geology, the relationships between the three main types of rocks. So those are igneous, metamorphic, and sedimentary. And because it's a cycle, it's kind of hard to say, where it starts and where it ends. But I like to think of it as starting with magma or lava if it's above ground. And you can see this arrow that goes from magma. Let me zoom in here, because this is the part that we're going to talk about tonight, which is different than most of Arkansas. Most of Arkansas is the sediments and sedimentary rock part. But this part here, from magma to cooling and forming an igneous rock. So that process, when I talk about this with my students at the university, I use the word freezing because that's really what it is. If you think about water freezing to form ice, magma freezing and forming crystals, just the same kind of process. In fact, the other thing I always talk about is ice. Is ice a mineral? Ice is a mineral. It meets all the definitions of a mineral. Okay, so it's a similar process. So think of this as magma freezing, cooling, and crystallizing to form igneous rock. So this happens in kind of two main ways. All right, so you've definitely heard of the first one, which is what we call extrusive or volcanic. This is when magma comes up through the earth and erupts on the surface as lava, right? And so this is very rapid cooling of this magma outside of the earth, okay? So the crystals just do not have time to grow big. They're very, very small crystals. In fact, sometimes they're so small that if you pick up a piece of rock, like here I use basalt as an example, it's too small to see the crystals with your eyes. Sometimes you can, sometimes you can't. I have a few rocks here. This one here is an example. This one has, sorry, I'll hold it up here. I know I got some pictures for you guys. Don't worry. This one is got some big crystals in it, but it also has lots and lots of tiny little crystals that you can't see. That's what most of the gray in this is. I'm going to hold it up to the camera. I don't know. I can't see myself on here, so hopefully you guys are seeing this. But this is an example of a volcanic rock. Okay. Fine. What's that? All of these are from Arkansas. Yeah. So you guys, I'm going to show these, and you can check them out. There's a lot of diversity in Arkansas. So it has a fine-grained texture. Now, the other way is when the magma cools underground. So in fact, here in the picture, you can see that magma chamber down there. So everything in that magma chamber, it both sends stuff to the surface and erupts, but it also cools and crystallizes underground. And that leads to the very familiar coarse-grained rocks that we think of when we think of igneous rocks, like granite, right? Or here in Arkansas, syenite, right? Which is what Granite Mountain, anyway, we'll get to that. Granite Mountain, Syenite Mountain, okay? So this is what it looks like, right? So there's a lava flow, and you can see even in this picture at the top on the right where you have solidified stuff, it just looks gray. You can't see the crystals. They're very, very fine. There's a chunk of granite by comparison. Now, these are obviously not to scale, but you can definitely see that this is filled with different crystals, right? Some black, some pink, some white, and other colors. If you look at it microscopically, these two rocks, this is what it looks like. So we use a special kind of microscope called a petrographic microscope. It has special polarizing lenses in it to let us look at these. We make these thin sections. My students right now are making thin sections. They're little glass slides of rocks. So imagine this, I make them cut the rock. They have to attach it to a glass slide with epoxy. They cut off most of the rock, and then they have to grind it down to a thickness of 30 microns. Do you know how many microns are in a 1 millimeter? 1,000 microns in 1 millimeter, and I'm making them grind it down. I'll look right into the camera. I'm making them grind it down to 30 microns. But when you get that thin, the light can actually pass through the minerals. It's really kind of a cool thing. And you get these kind of really cool colors. It is. That's exactly what it is. It's wow. I did birefringence. That's great. Yeah, these are interference colors in cross-polarized light. There's a lot of words and stuff that I could throw out, but what you're seeing here in the top is a lot of the black is actually glass in a basalt. And then you have some tiny little feldspar crystals and maybe a bigger olivine crystal there in the upper left. And then in the bottom, you have quartz and micas and hornblends and stuff like that. So, all right. So where do these things form? Yeah, was that the next question? Good. Okay. You know, it all comes down to tectonics, plate tectonics. So we have these plates going around, you know, crashing into each other, moving apart, sliding against each other. This picture shows some of the main places where these igneous rocks form. So I want to kind of walk you through this a little bit. On the left side of this image and the right side of the image, in both cases, you have a tectonic plate that is going down into the mantle. That process is called subduction. Okay, so you can see in both cases here, we have oceanic plates that are going down into the mantle. And what happens is as those plates go down into the mantle, they release stored fluids, stored water. And that water interacts with the mantle rocks and melts them, partially melts them. It's actually kind of similar to adding salt to an icy sidewalk or something. What you're doing is you're actually making liquid water stable at lower temperatures. So it's what we call flux melting. And water in the mantle does the same thing. It melts the rock and that forms magma, which then comes to the surface. So the example on the left where it says island arc plate subduction, the place you know in the world where this is happening is Japan right now. So the Marianas Trench, that big deep trench, and some of those islands, this is where you have ocean plates kind of colliding and subducting, and that's one. And then the place where this continental plate subduction is happening is very familiar to you too. This is like Mount St. Helens and the west coast of Washington State. So there's a plate there called the Juan de Fuca plate that is going down. It's actually from your point of view. Sorry, I'll stand back so you guys can see. It's going down underneath the North American plate. And then above that is where we're getting some volcanoes like Mount St. Helens and Mount Rainier.
So is the water hot? Is that why it's melting the rock?
Well, it is heated as it goes down, definitely. And it's so hot, we don't even think of it as a gas. When you reach a certain temperature and pressure, the gas and liquid water, sort of that distinction go away, and we call them fluids, and they have all different properties. It's really kind of interesting. But yeah, it gets very warm, very, very, we're talking as you're going down, 5, 6, 700 degrees, 800 degrees Celsius, right? It gets warmer and warmer as this is going down. Yeah, very, very warm. The other places in the middle, where it says plate divergence, this is where two plates are separating from each other. This is happening right now in the middle of the Atlantic. So Africa and South America and North America, they're moving apart from each other. Okay, so, and then we have these weird things called hotspots. And the place that's very famous, anybody know the hotspot place that's famous in the United States? There's two, actually, real famous ones. Yellowstone is one. And then, what's that? No, Hot Springs is not a hotspot. Yeah, Hot Springs is interesting. It is not related to magma.
No.
And I should let like Reed and Darsha talk to you about that because they're like, I can see them itching. They want to. It's just that the water goes down and comes up along a fault, and it gets warmed as it goes down. It comes up really fast. So, well, I say that it goes down and comes up fast. It takes 4,000 years for that water to go down and come back up. But anyway, geologically speaking, it's a blink of an eye. Yeah. Hawaii is the other one. Yeah, yeah. So those are both hotspots. So, and that's interesting. It turns out that maybe some of this is related to igneous rocks in Arkansas, but it's probably something different. There's still confusion about why we have the igneous rocks we do. One idea is that when these rocks here were forming, it was because the crust was trying to split. So it was trying to diverge. And it actually kind of went through time number 1 in this picture, time number 2, and even time number 3, where you can see some little volcanoes and stuff coming up. But it didn't go all the way. It didn't keep splitting. So that might be one theory. There's a theory, there's this theory that there was this mysterious hotspot called the Bermuda hotspot that may have traveled through and under what is now Arkansas. People don't necessarily believe that. Even if there was this hotspot, it didn't follow the right path and things like that. So the place where this is happening in the world today, what happened to form a lot of the igneous rocks in Arkansas, is happening over in Africa, in the East African Rift. And so this is an example of a rift zone, and the Red Sea and the Gulf of Aden are actually successfully splitting and forming new ocean. So there will be, as the Arabian Peninsula moves away and the rest of the African continent moves away, that Red Sea will get wider and wider and one day be an ocean. And same, with the Gulf of Aden. So these things form as triple junctions, and the third part of it is going down through the African continent. And there's a lot of sort of famous places here, like Mount Kilimanjaro, Lake Victoria, and things like that. This is what Arkansas would have looked like when the igneous rocks here formed. This is what we think. So
that section of the Gulf of Aden is actually moving away from the main.
yeah, so
Getting 3 things.
yeah, exactly, right. Sorry guys online, I'm using my hands in the screen, but like this part where Mount Kilimanjaro, Gulf of Aden is written, this is moving kind of this way to the east. This part of Africa is moving to the west, and this is kind of moving up. So this is splitting, this is splitting, this is splitting. Yeah.
So New Madrid is a failed rift, right? Is that
Right. So this is so the New Madrid seismic zone is part of what is this thing called the Reelfoot Rift, or it's reactivation of faults along the Reelfoot Rift. And so that rifting is probably related to the igneous activity that we have here in Arkansas. So I'm going to tell you the times in just a second. We're almost there, but I'll give it away. This all happened like 100 million years ago, right? So it's been a while, but still today we have like this New Madrid seismic zone. It's still active, right? So we have the modern day stuff still going on. Geology doesn't stop. It just keeps going, right? So, okay. So I talked to you guys about what is a rock, and I talked to you about what is an igneous rock. Now I want to talk to you about what is an Arkansas. That was my title. Okay. So what is an Arkansas? Well, if you ask a geologist, this is an Arkansas. Okay. This is the geologic map of Arkansas. I'm sure you've seen this before hanging up somewhere. It's got lots of colors on it. This is a pretty complicated map. The colors on this map represent both types of rocks and ages of rocks, right? And so, and then of course we, and I know this is familiar to most of you in this room, this state is divided into these physiographic provinces, the Ozarks, the Arkansas River Valley, the Ouachitas, the West Gulf Coastal Plain and the Mississippi River Alluvial Plain. So everything you see here is really defined by sedimentary rocks, pretty much, right? The Ozarks, you go up to the Ozarks, what is it? Fossil land, right? You can go in caves, and it's all limestone up in the Ozarks. And then the Ouachitas, a lot of shale and sandstone and novaculite and all those interesting things. Gulf Coastal Plain has gypsum mines, and it has other fossils that are younger in age than up in the Ozarks. And then the Mississippi River Alluvial Plain is a lot of sediments, and it's very important because that's where all the farming happens, right? And there's a lot of groundwater. And anyway, so very important stuff. When it comes to igneous rocks, though, here's the map of Arkansas. Right? So you asked me to talk about igneous rocks, right? So and now there's more than just what I have on this map, but this is the main stuff I wanted to talk to you guys about was these kind of three places that we have igneous rocks. So this collectively, oh, here's the ages. I forgot, I put the ages on here. So Prairie Creek lamperite, also known as Crater of Diamonds, Magnet Cove alkaline intrusive complex, and then the cyanites that are in both Saline County and Pulaski County, right? Granite Mountain. So you can see something interesting in the ages. They're all what we would say is from the Cretaceous period, right? So the Cretaceous period ended 65 million years ago with some kind of important event. I'm not exactly sure what that was. You guys know what happened 65 million years ago, right? So yeah, it's a mystery. Yeah. So this is mid-Cretaceous. So there were dinosaurs roaming around while this was going on, is kind of the point, right? So what's interesting is the Prairie Creek is the oldest, and there's sort of this younging trend as you go up to the north and east. That's kind of interesting. Not sure exactly if that's related to rifting and extension of the rift to the northeast, possibility. So this collectively is known as the Arkansas Alkaline Province. These bodies, they're all very unique rocks, and I brought a whole bunch here. And so this is really what I want to talk to you guys mostly about. If I have any time left, I've been going, oh, I've got it.
Okay.
Yeah. So the Arkansas Alkaline Province comprises, these things, and then there's other weird, there's these Lamprofere dikes in Benton, and there's other weird igneous rocks that poke their head up in this sort of area. I'm going to focus on these three because well, they're well known to us, right? I'm sure all of you have probably been to Crater of Diamonds, definitely heard of Magnet Cove, and then of course the cyanites are everywhere here. So you'll notice it just marks here in red that they're the igneous bodies. And then, like I said, everything else around it is all sed rocks. So I don't like slides with a lot of text, but there's a really good researcher who worked on this area called Eby, right here is his last name. And I actually liked what this little paragraph. So I wanted to read this to you. And I'm actually going to read it. I'm going to read a slide. I'm breaking all the rules right now. The intrusives of the Arkansas Alkaline Province lie in a northeast trending belt along the northern edge of the Mississippi embayment. So right here, it says Gulf Coastal Plain, but this is right Mississippi embayment here and Gulf Coastal Plain kind of going through here. There is a spatially related variation of lamproites, Prairie Creek, that's also Crater of Diamonds, and at the southwestern end through several carbonatite complexes. I had never even heard of a carbonatite before I moved here. This is not carbonite, the stuff that Han Solo got trapped in. I just want to be clear about that. It's not carbonite. Anyway, I just watched Empire Strikes Back was on TV the other night. So, and a Lamprofere dike swarm in Benton, and at the northeastern end, several large cyanite bodies, Saline County and Granite Mountain. Lamprofere and cyanite dikes outcrop at the V intrusive and carbonatite dikes are found at Perryville and Morrilton, which is interesting. Drilling has revealed, and I bolded this, significant amounts of subsurface carbonatite, Lamprofere, and cyanite. So even though we have these little outcrops, these dots, there's probably a lot more at depth. A lot more at depth. So what I'm going to do now is just kind of step you through each of these three areas. And I thought I'd start at the bottom with Crater of Diamonds and work our way up towards Little Rock. Okay, so we're going to start here. We're going to start with Prairie Creek. I'm just going to throw this back up to remind you. So I actually brought some diamonds from Crater of Diamonds. I don't know, I'll pass a couple of these around if you want to take a look. Here you go. For the video. Here, I'll start over here. I don't know where these came from. I mean, the names of the people who found them are on there. I just acquired them at the university, and I've been kind of keeping them in a cabinet and stuff. Have any of you found a diamond? No, of course not. Because you're not no, what I say is, the reason is you have to be like 10 or 11 and really close to the ground, and you have to like be on a family vacation and only show up for like a day and find them. Actually, it's crazy. I just had a conversation with a prospective graduate student who lives here in town, and she moved here. I hope she doesn't mind me telling you this, but she moved here because she and her fiance were very interested in going and looking for diamonds at Crater of Diamonds. And she told me they have gone 3 times and they have found 7 diamonds. Now I have to find out whether she's lying or not. But I actually have a picture of my first time at Crater of Diamonds coming up. It's a great place to go spend some time, and maybe you'll find a diamond, but it's really hard to do. And the best advice, of course, and I'm sure you've heard of this, go after a rain, so everything's sort of washed off, and that's your best chance to find one. But so this is kind of just a map of the area, sort of the boundary of what they say on this map, the volcano boundary. And I just pulled this off the web, but it shows like all the washing pavilions and the places to dig and where there's been drill sites. This was actually drilled to see if it was economically viable, right? And there's just not enough of a concentration, at least in those drill holes. I think this was back in the 90s, maybe even earlier, when they did this big sort of drilling program. I actually have the reports. Mike Howard, some of you probably know, retired geologist from the Arkansas Geological Survey, shared a bunch of stuff with me as he was retiring. So this is what this place looks like. You notice, oh, I forgot. This is my picture, yeah. Look at how interested all my students are. And then this is me, pre-beard. It looks like I spent the whole day and I found nothing. No, I was here for what? 2 or 3 weeks, and everybody from home, from Wisconsin, was like, "Did you go look for diamonds yet? Did you go find diamonds?" I was like, "No, not yet." No, I don't know. Maybe Corbin was on this trip. I can't remember. But we spent the day out there. Everybody had a good time, actually. But I tell people, if you really want to find something and take something home, go dig for quartz crystals, because you're definitely going to find something if you do that. But so this is what this lamproid Prairie Creek looks like. And you notice here it says schematic cross-section of the Prairie Creek diatreme. I don't know if you've heard that before, but diatreme are these it's either a lamproid, or the more familiar name that you may have heard of is kimberlite. Probably heard of kimberlite pipes. But the idea is, if you notice, there's this tiny little conduit here, this little conduit that goes to the bottom of the picture. It doesn't stop at this depth, whatever this depth is here. It says 950 feet or something. That conduit goes all the way down and through the mantle. It's believed to go as deep as possibly the mantle core boundary. So these things are derived from very, very deep. And then to get these things up to the surface and actually preserve in them the diamonds that you're looking at, these have to erupt to the surface at incredible speeds. So people estimate these are like supersonic speeds. So faster than the speed of sound coming up to the surface. I've never seen one. I don't think we've experienced one in sort of the human history. What the big difference between a lamproite and a kimberlite named for Kimberley, South Africa, lots of diamonds found there, right? The big difference is what you notice in the shape of this. Now, this is a cross section. It comes up to the top. These lamproites interact with groundwater and have other fluids. And when they get to the top, they explode out. So it gets this real like sort of martini glass shape, or kind of looks like a funnel. And so this is what Crater of Diamonds, this is what Prairie Creek looks like. Now you'll notice there's some different words here: magmatic lamproite, pyroclastic lamproite, tuff, mar epiclastics. When you see words like pyroclastic and tuff, that means volcanic, right? So these are similar to, you know, volcanics. So here's an example of what a lamproite is. I have some other pieces over here that you guys can take. I'll just pass a couple around. Here's some lamproites. Here's some other. I actually have. If anybody has a tweezers and you want to start going through this bag of sand this is from Crater of Diamonds, maybe you'll find a diamond in there. This is what a lamproite is. It's an ultra-potassic mantle-derived volcanic or sub-volcanic rock. It has low calcium, aluminum, sodium, high potassium, relatively high magnesium content, and extreme enrichment in incompatible elements. That means elements that don't easily fit into mineral structures. So some of the minerals that you will find there, this is the one that I study a lot, olivine. You guys probably know olivine by a different name. Peridote. That's peridote and olivine. Anybody here, August, that's your birthstone. Okay, so you can find lots of olivine in these rocks. Leucite, phlogopite. Phlogopite's a mica mineral. Leucite is a weird mineral. It's called a feldspathoid. It's a weird one. Richterite, diopside. Diopside actually looks a lot like olivine. It's kind of greenish in color. And sanidine. And then also garnets. I have found garnets when I was at Crater of Diamonds. And this picture back here, I'm just going to go back for a second. This is Margie Jenks, who I met. This was years ago when she was working at the park. She actually gave me a vial of garnets that she had saved, and I still have that vial in my office that she had found at the park. And it's surprising people don't think that they would be there, but she found a whole bunch. And sometimes diamonds. This is a big picture of what an olivine lamproite looks like. So these are the olivines in here, right? These things, they're kind of weathered out. They don't look like that vibrant green that you're used to for other olivines. But anyway, that's a big picture of what a lamproite looks like. So this area, Crater of Diamonds, is not the only one of these pipes that is down there. There are others that are probably diamond bearing, but they're on private land. So it'd be interesting to kind of explore this a little bit more. But anyway, so there's a little bit about Crater of Diamonds and the rocks that you have there. Let me check on time. I don't want to go over. Yeah, so I'm going to move on to Magna Cove. Okay, so I put this map up here. This is, I actually brought this along. This is a publication from the USGS. What's the date? It was in the 60s sometime. Like it's this really old publication. And you know, I'm sorry, 60s. For me, that's but I brought this along because this map was by Erickson and Blade, and it's like one of the most important studies done of this area. And I actually brought along, you gotta be careful with this, but I brought along the actual map from the publication. So we can look at it later. I'm gonna just leave it over here. We'll unfold it later. You can see it on the screen. It's very vibrant with color, which means that there's lots of different things going on in Magna Cove. So one of the things, let me go to the next slide. So this is Magna Cove is kind of located. This is like I-30 right here on kind of the right where the orange and the yellow is, that's pretty much where Interstate 30 and Malvern, this is just west of Malvern, right? So there's Magnet Cove and Potash Sulphur Springs. Here's all of the zigzag mountains you'll see here, Mississippi and Silurian Ordovician. All of the surrounding rocks are like anywhere from 400 to 300 million years old, maybe even a little bit young, maybe 280 or 300. The Magnet Cove rocks, at least 100 to 150 years, 150 million years younger than everything else in that area. And so they intruded what was already there, right? And you'll notice something interesting about this map. You can see sort of the zigzag of the zigzag mountains. And if you notice where Magnet Cove is and where Potash Sulphur Springs is, they're both at sort of the bend of the zigzag, right here. And so these are folds in the mountains. And so they're probably areas of weakness that the magma was able to come up through. So it's kind of interesting. So to me, it's like, well, if I was looking for more things like this, maybe I would look at the nose of this thing, or the nose of this thing, or the nose of that thing, right? Because it seems like there's some correlation there. So here's a detailed map. Now, this is all from the Arkansas Geological Survey. I shamelessly stole this, but I credit them here. So it's a really interesting, dynamic place. People come from all over the world to look at these rocks because they're unlike, like, there's only a few places where you can find these rocks. So here's the story. These rocks, this is called an alkaline intrusive complex, right? And so alkaline in this context means silica deficient. So most igneous rocks have a lot of silica in them. And they have so much silicon in them, silica, that they form all the minerals that they need to form. And when they have silica left over, they form quartz, right? And so that's most normal granites, right? If there's I don't have a chunk of normal granite, I should have brought a regular granite along, but most granites have quartz, right? These rocks, no quartz, right? The syenite that we're going to talk about in Granite Mountain, no quartz, or very, very little quartz. They're what we call silica undersaturated. They had enough silica to make some of the minerals, but not enough left over to make rocks with quartz in them. In fact, Magnet Cove was so silica undersaturated, it actually, before crystallization was finished, it ran out of silica completely and crystallized something else. And that's kind of the story here. So the other thing is, you notice there's sort of a ring shape to this. You see the ring? So you have the yellow around the outside, you have the green, and then you have this other yellow shade that's labeled, looks like an eye here. And then you finally have these labeled with C in the center. This is what we call a ring complex, right? So what you have to imagine, and so I don't know for sure that there was a volcano above this, but that these are subvolcanics. So these were probably in place below ground, right? They were definitely in place below ground, but maybe kind of near the surface. We're not really sure. But these are the magma chamber crystallizing things and other stuff getting injected in. And so lots of interesting things going on here. The yellow, let me go to this next slide. So the yellow around this outside is got, it's labeled S. It's mostly cyanite. Okay, so similar to Granite Mountain, but it's got a little bit more going on. So this is a piece of nepheline syenite. What's really cool about this one in particular comes from a quarry called the Diamond Joe Quarry. It actually has this cool bluish purple sodalite on it, which is, if people really love collecting this stuff. So I'm going to pass that one around too, if you want to take a look at that. And then, so the thing about Magnet Cove is it has all these weird names for the rocks that I've never heard of. Like, you guys have heard of granite, right? Maybe you've heard of basalt. These are the normal names. You come here, and then it's like Here's a rock called jacoporangite. Like, here's a rock called igellite. And I'm like, I've never heard of these things. So they're named for very unique places. So the rocks are super, like this one, I'm gonna hold this to the camera if you guys can see that. This one is one of my favorite. This is a type of garnet biotite igellite, but this one just has these beautiful aqua colored phlogopite micas in it. This rock is beautiful, and it came out of a ditch in front of a church in Magna Cove. It's like, everybody knows Corbin's laughing right now. I know he is, because he and I have spent quality time in that ditch. I'm telling you, he spent more time than I have. He's, you know, if you want Corbin, if you want somebody to really tell you about Magna Cove, get Corbin to do it, because he knows all about it. But this is, it's a beautiful rock. People drive by it every single day. It's got really cool black garnets in it. Very unusual garnets. Most garnets are red or orange or green. Magna Cove, they're black. So they have like titanium in them. There's a special type of garnet in Magna Cove called Kimseyite. It's named for the Kimsey family and the Kimsey quarry. It's a zirconium garnet. It was first found in the entire world and named for this place in Magna Cove, right? First, it's the type locality for that type of garnet. So anyway, I gotta pass this one around. I'm gonna start over here this time, just to be fair. You wanna start? Oh, you wanna, oh, yeah. Is that in the board? Yeah, sure. There you go. We're not sharing. You're not sharing, good. Okay. Just keep it. Yeah, everybody break off a chunk on the way. No, I'm just kidding. No, it's really, that one's so pretty. I'll tell you where to go. You can get your own. So yeah, so the thing is, there's all these interesting rock types in Magna Cove, and I just wanted to, I'll throw a few pictures up here. This is mostly for you guys on Zoom and also for you in the room, but I had the hand samples, but I also wanted to show you these pictures that I'm showing you are pictures of rocks from Magna Cove, from Arkansas. Okay, so it's not labeled there, but these, and this, I found this, to be honest, I found this guy on this website where he took fantastic pictures. So this is the Nepheline syenite that you get. This is phonolite, and I actually have a piece of this right here. So this is phonolite. Looks kind of the same. Okay, so I'll pass this one. This one's got some cool flakes of mica that you can see. This one's a volcanic rock. So it's like there was volcanic activity. This rock proves it. It was actually misidentified at first, and then they came back and realized it was a volcanic rock. Here's the jacoporangite. I had a friend. I have a friend who's a professor at UNC Asheville. Her name is Jackie Langiel, and she and I went to grad school together. And I brought her to give a talk, and we went out to Magna Cove to look at the rocks. And she decided that this was called jacoporangite from now on. So every time I see it, I think of jacoporangite. This one has a lot of pyroxenes in it. It also has a lot of magnetite in it. Sometimes some pieces of this, actually magnets will stick to it if you get the right piece. Here's the igellite I'm passing around right now. Lots of micas, lots of garnets, feldspars, other weird things, all sorts of interesting minerals. But probably the thing that I really think is most interesting about Magna Cove, this is my personal thing, is this last one, this carbonatite that I mentioned. So this is, I got a couple chunks of carbonatite. Okay, this one's pretty big. Start here. This one's a little bit smaller. This is a mineral, this is a rock. Carbonatite. Okay, where am I starting? You again, you're gonna pass it. Okay. This is a rock made of the mineral calcite. You guys know calcite?
Chalk. Yeah.
Yeah, it's like chalk. It's like usually you find calcite in limestone. This rock made of calcite, and there's other things in there too.
Those are little red things.
Oh, those are those look like, I think those are actually pyrites.
Pyrites?
Yeah, I think you got little pyrites in that piece. Yeah, little fool's gold. This calcite actually was formed from a magma. This is very, very unusual. Most magmas, like I said, they're silica rich. This is what I was talking about. So let me go back to this picture right here. This carbonatite is this real light yellow stuff where it says the Kimsey calcite pit. And there's actually, you can drive right through it. There's the stream goes, there's Magnet Cove Creek or whatever goes right through here. You can drive right through there. There's an outcrop of this stuff, and it's calcite that was crystallized out of a magma. This doesn't happen anywhere except for maybe underneath Mount Kilimanjaro right now and a few other places around the world. Very unusual. This Kimsey calcite pit is where that kimseyite, that zirconium garnet, was found. You find really interesting and weird minerals in here. Vesuvian. In fact, let me show you some of these. I got a picture of some of the cool minerals you can find. So the thing is, like, igneous rocks, the igneous history is really interesting because it was this really silica undersaturated. What people go to Magnet Cove for is this. They go to collect the minerals, right? So eudialyte, this pinkish mineral, you can find that kind of near the carbonatite. Vesuvianite, also known as idocrase. Magnetite, of course, that's where Magnet Cove gets its name. There's a spot where we stop and we stop in somebody's driveway and we just run our magnets through the gravel. And it picks up magnetite. It's just there. It's just there. And brookite, these are rutile paramoid. So that this is actually rutile, but it has the shape of brookite, which is a titanium oxide mineral. So there's, I mean, people love going to collect in the cove. How am I doing on time?
You're okay.
Okay. Okay. Oh, geez, 7:30 almost. Okay. So if you haven't been, what people do is they put on waders and they go into the creeks and they dig around for minerals, and you can pull out amazing stuff. I mean, there are places in the cove where you can go and just dig around in the dirt and you're pulling out pyrite crystals left and right. There's all sorts of really cool, it's a really cool place. There's a quarry, the Martin Marietta quarry is just on the south side on 270. If you've ever taken that road, that's actually Stanley Shale, which has been metamorphosed slightly, so it's a little bit harder. And then just adjacent to that is an old quarry called the Diamond Joe Quarry, which, if you can get into, is a real treat because there's some really cool. That sodalite piece that I passed around is from that Diamond Joe Quarry. So,
And Michael, that
Yeah.
would actually make a good master naturalist field trip.
I would love to take you to.
That would be great.
Yes, Corbin, you hear that? They want to go to Magnet Cove. He's run so many field trips that he and I can run it together. It's a great place to go. It really is. Best time of year, I would say, you know, probably in the early spring when it's like not too many bugs yet and not too much leafy stuff. You could probably see more. You know, this carbonatite is right on the road. The Kimsey family was so upset that people kept stopping there to collect and stuff. They actually spray painted it and tried to camouflage the outcrop. And then all of that's worn off now. It's gone. But it was like, you know, people really do like to go into Magnet Cove to collect. And so you have to talk to the homeowner because it's all privately held. It is a spot. I will say this also. It is a spot that contains a lot of rare earth elements and things like that. So I wouldn't be surprised if people take a closer look as we're trying to find these critical minerals, take a closer look at Magnet Cove, unfortunately for the people who live there, you know. But anyway, okay, so yeah, we got to go. Yeah, let's go. All right, so I'm going to go quickly through this because we're kind of getting low on time here. But the last place I want to talk about is close to home, is Granite Mountain. This is the quarry that I didn't know what it was when I first arrived. Now I do. I've been there several times. Granite Mountain should be called Cyanite Mountain. Okay, well, is that a big deal? Not really. So the way this thing forms, and I'm just going to show you this kind of like, this is what I teach my students. These are the magma chambers that are underneath volcanoes. So this is time one, right? So if you go forward in time, after the volcano sort of shut off, the source shuts off, you have this cooled and crystallized stuff down at depth. And as you either uplift it or weather away the stuff on top, eventually it gets exposed at the surface. And this is the status. This is where we're at now with Granite Mountain. It's up at the surface. If you've never seen it, go to Audubon, right? You can walk on Nephilim Syenite there, or just drive down the I-530. It's on the sides of the road. Or pick up any piece of gravel in this city, right? Because we use it everywhere, right? So, I wanted to show you this because this is the classification diagram that geologists use for all these sort of igneous rocks we've been talking about. And this is quartz at the top, alkali feldspar, which is the pink stuff in a granite. This is plagioclase feldspar over here. And then this F stands for feldspathoid. For us, that feldspathoid is nepheline, which is it's kind of what gives the bluish kind of color to the syenite that you see. So granites plot up here. They have quartz in them, right? So everything above this middle line, silica saturated. Everything below the middle line, silica undersaturated. Doesn't have enough silica in it. This is where our rocks plot, right down here below where it says void-bearing syenite. They're down in there. Very unusual. This is like Pikes Peak, the Sierra Nevadas, Stone Mountain in Georgia. All of those plot up here in this granite up on the top of this diagram. It's very rare, very few things that plot down here in the lower part of the diagram. So it's kind of cool to have this in our backyard. It's still just a rock. I'm a rock guy, but I'll say it's just a rock. But this is kind of the deal when it comes to this stuff. So here's our rock, right? Velasquite is kind of a name for it. Yeah, did you guys know that?
No.
This is kind of, it's written up there, but it's kind of hidden by that little thing. But this is the main stuff, so it's this guy right here, right? This if you haven't seen this and you live in Little Rock or the surrounding area, I would be shocked. It's everywhere. It's everywhere. We use it for so much. If you break this up, they dye it and use, 3M Quarry dyes it to make the grit on shingles, and stuff like that. It's a nice rock. If you go to, we go over to Mount Holly Cemetery with our students and look at the gravestones, and you can tell people with money, this stuff, people without, limestones and stuff like that. And so we do a whole weathering thing because we look at the limestone gravestones versus these, where they last for a while. If you want to take a look at that. But it's not just this stuff. You get some really unusual rocks. This is another one from this is from the quarry. And then I brought some other ones here. This stuff, right? This is from the same quarry, Granite Mountain Quarry. Kind of hold it up to the camera here if you guys want to see it. This has these weird bladed agerine pyroxenes in it. It has calcites in it. It has weird stuff. People come from all over to dig through this rock to try and find minerals that have never been found before. And there have been a bunch found in these rocks right here in the Granite Mountain Quarry. So it's trying to see if I'm going to pass this around. Sometimes if you look in some of the little holes, you can see tiny little needles. I don't know if this one has it or not, but kind of bring this past the camera right by. There we go. There's another rock here. I just keep giving them to you. I've known several geologists from Arkansas who are interested in Arkansas rocks and minerals who have since had minerals named after them. Some of them are still alive, some of them have passed. The guy who taught mineralogy and petrology at UALR for 22 years, my predecessor is a guy named Don Owens. I don't know if any of you ever knew Don, some of you did. There is now a mineral called Don Owensite. It's pretty cool. There's a mineral, there's a really great guy named Henry DeLindy who owned that Diamond Joe Quarry I was talking about. DeLindyite is a mineral. There are only 5,500 known minerals. Mike Howard, retired from the Arkansas Geologic Survey, Mike Howardite exists in the world. It's pretty cool. You can't name them after yourself, but somebody can name them after you. And one guy who I was fortunate to meet, really great guy from Troy, a guy named Henry Barwood, used to come up all the time to Granite Mountain quarries to look for minerals. Barwoodite is out there. He gave some really cool talks talking about using fluorescent lights of different wavelengths, and these rocks glow and all sorts of things fluoresce in them. It's really kind of cool. So people come from all over the world to look at this stuff that we just use for gravel in our driveways and stuff like that. Okay, so the last thing I wanted to say, I have one slide left, okay, is underneath all of this sedimentary cover, if you go down far enough, are more igneous rocks. So all of Arkansas actually has igneous rocks. You just can't see them. But if you go down deep enough, you can. Or if you do this, you can see what's underneath Arkansas. And that's go visit our neighbor. This is kind of blurry, sorry. But if you go, and some of you have probably done this, if you go up through the St. Francis Mountains, the red stuff in here are really, really old, 1.5 billion or older igneous rocks that are exposed at the surface. They're granite. So if you get up there, there's some really great, I take my students up there every spring. Elephant Rock State Park. You can walk around giant boulders of granite. You can walk on the giant house-sized boulders of granite. There's rhyolites, which are volcanic rocks. There's basalt flows. There's even, if you guys know the Led Zeppelin album Houses of the Holy with the columnar joining, you want to see that? There's a place called Hughes Mountain Natural Area up in Missouri that has columnar jointing just like that. It's really, really cool. So if you want to see the stuff that's under Arkansas, you can go and see it up here. We just don't have it exposed. But all of Arkansas has igneous rocks. It's just a few places where these really interesting rocks have come to the surface. So anyway, definitely gone over time. Love to answer any questions. Thank you all for having me. Appreciate it. Thank you.
Let's see, chats.
Okay.
Any questions?
And we got a question. I'll start with you. Sure.
Okay, so Magnet Cove is mostly private property.
Mhm.
Will 3M give you grief about stomping around Granite Mountain?
So actually I haven't been to the 3M, but Granite Mountain Quarries, I've gone there several times. They're actually, if you just call them up, like if you ever wanted to do a field trip as a group, there's some really great people, and I can get you connected with them. When you do a field trip at Granite Mountain, if you can time it right, you time it for a weekday when they're going to do a blast. And let me tell you, it really is one. It's a blast. So what they do is you put on the hard hats and everything, and you stand on the opposite side of the quarry. And there's like the alarms go off, and then everything gets quiet, and all of a sudden you see the rock blow up, and then you hear it and feel it, and it's an amazing thing. And then they usually let you go around and pick on the rocks after they've done it, right? So as long as you don't get too close to the loose stuff. But no, they've been really generous. We go there, we go to Granite Mountain. I have colleagues. There's a professor at Stephen F. Austin who's a good friend of mine. Her name's Leanne Stevens. She brings her class every year. She comes up, they go to Granite Mountain, they go to Magnet Cove, they go to all these places. And so people come from all over to stuff that's in our backyard. The really cool thing at Granite Mountain Quarry, if you can arrange it, is you can pick through the rocks and look for minerals, and you find some cool stuff. But then they'll also show you the crusher. You guys know what a mortar and pestle is? Yeah, think about that like on steroids. I mean, this thing is giant, and they're huge boulders that they're sending through, and it just crushes these. It's really kind of cool to see. So yeah, Granite Mountain Quarries would be a great trip. Yeah, there's a lot to do. I mean, you can see the rocks exposed if you just go to Audubon. If you go to the center and you do the hike there, you'll see it exposed. But it's nice to really see really fresh cut, fresh exposed rock, because then you can find the cool minerals and stuff in it too. So, all right. So were there chat questions?
No, there was.
Are there any questions from anybody online? Other questions in here? Oh, you just got a rock?
Bert has a question.
Oh, okay. Do I have to do anything or can he just
No,
speak?
just Bert,
He
You got a
needs-
question?
He needs to unmute himself.
He's
yeah.
muted.
Oh, Bert, you're muted. Did you have a question?
No, I was just waving, saying, no, I don't have one.
Okay, okay. Yeah.
The
Mhm.
mining for that, any thoughts or?
I think it's gonna
why
be,
is it there?
well, it's sort of, I don't know a
Can you
ton.
repeat the question for the.
Yeah, so the question is about lithium and mining of lithium. And to be honest, I don't know a lot about it. I'm about to because I have a student on it in a few weeks. So I'm really excited. I think that the lithium is part of the brines that are down in depth in sort of as you get into the Delta area, right? So it's in southern Arkansas. I think it's going to be a huge thing for Arkansas, actually. I mean, good or bad, right? I mean, do you really want that kind of mining? I mean, we have a lot of, our number one thing that we mine is sand and gravel, right? Gravel, that's mostly what we do, but there's tons of different kinds of mining already in Arkansas. Everything, like I said, the gypsum mine where they make drywall and sheetrock and stuff like that. So what's it? Bromine, yeah. So, yeah, maybe other people in here know more about it, but I think the thing with lithium, I don't know if you remember a while ago in the talk, I said something about incompatible elements. And lithium is one of these elements that doesn't fit into minerals very easily. The mineral that it fits into, that's kind of the most well-known mineral, is called spodumene, which is and it's usually those minerals are found in rocks called pegmatites. And pegmatites are these rocks that have really big crystals, really big crystals. So there's kind of a famous place in North Carolina, which of course the name's escaping me right now, where they mine for this pegmatite. And I think they're pulling lithium out of there. But to get then lithium in these brines and things like that, I mean, it's going to be, because all these batteries and all the materials that we're using are using lithium, right? So I think it could be a big thing here, but I don't know enough about it yet. So.
So I wondered if this was an AV.
Oh, you brought a rock. Okay. Let me take a look. No, but it's like got a lot of quartz in it, but I don't think it's an igneous quartz. I think it's probably precipitated quartz. But I don't know, got some weird textures in there.
That's what I looked at.
Yeah.
I said,
Yeah, I don't know. If you want to, you should show this to everybody. It's kind of cool. It's got something metallic, but I think it's probably a little bit of the iron that we get in some of the sandstones in Arkansas. So if you've ever been to, I know you guys have been to Petit Jean. Petit Jean has a lot of these iron bandings and things like that through there. And I think that's kind of related to that rock. I see some iron in there. So we have these things called Lisa Gang bands that form, and you get these iron concretions and stuff. It's one of the biggest parts of my job is, and by the way, you're all welcome to use this. On our website, we have an identification request little screen. So if you have a rock that you want to know about, put your name, put a little information about it. Those emails come to me. And then I will write you back and say, no, it is not a meteorite. So you guys know all these like weird iron bearing things we have in Arkansas, these roundish things, people think they're meteorites and they ask me about it. And I have to say, unfortunately not, but, concretions. Yeah, exactly. But then having said that, meteorites have been found in Arkansas, so it's not impossible. But anyway.
Have you looked at the iron ore up in Wisconsin?
Yes. Yeah. So Wisconsin, I ran a class a few years ago, and I really want to run it again. It was called Geology of the Upper Midwest.
Mhm.
And it's great because we went all through Wisconsin and went into the UP. And so I've been to the Republic Mine, and there's a really great, if you ever go, my favorite outcrop in the whole world that I've been to so far is in Michigan, in Ishpeming, Michigan. Have any of you ever heard of Ishpeming or been there? There's a hill called Jasper Knob in the middle of the city, and it is it's all banded iron formation. If you've ever seen banded iron formation, it's got red chert with specularite hematite, the really bright, sparkly hematite. This entire outcrop just sparkles in the sun. It's beautiful. But yes, I've been up there. They're actually a lot of reprocessing of old mine of the taconite, the really fine grained iron. They used to just go for the real easy iron, but now they can get some of this iron out of the sediments and stuff now too. So it's kind of been a rebirth a little bit of some of the iron mining up there. But yeah, it's a very different world up there. So yeah. All right. Well, thank you all. Really appreciate it. Come look at the rocks if you want. And thank you guys online. Sorry if I had my back to you most of the time.
So would you like a Lowe's gift card or a Lowe's gift
Take a
card?
Lowe's gift card.
Here you
Yeah,
go.
thank you. That's so nice. I'm fixing my house, so from the tornado still. So this is help. Thank you.
These are all.
Goodbye, everybody. Oh, wait, we got a chat.
Yes, these are all, thank you. This one's over here.
I see you. Thanks, Steve.
Some different types.